Okay, now this will be the we'll be discussing about the interference in wedge-shaped thin film. So the name of topic will be interference in thin wedge-shaped film. So what is that film? The film is the air. So how do that wedge-shaped air film can be obtained? So if you look at the diagram, look at the diagram. So I'll take the two glass plates. Let me make a small angle of inclination. So there's a lower glass plate. On it, I'll keep another glass plate. And let there be a wire be placed at one end. At other end, these two will be in contact. These two plates will be in contact. This theta will be very small. I think I'm writing wire. This will be more than enough, like a thread, wire, or a paper. So like that, let me place here. So because of that, a small inclination will be formed by the upper glass plate, this one, and the gap between these two glass plates will be an air film, and the air film, how it is in the form of a wedge. These are not glass rods, glass plates. They are glass plates. Let me glass plates. So how the air film will be of this, so therefore it is called like a wedge. I think that these are called like a wedge. I think in Newton's laws of motion, we called them as a wedge, no? So the air film will be in the form of a wedge, no? Got it, no? So what is our purpose? I want to find out the diameter of wire, or I can keep a piece of paper between the glass plates. So how to find out that particular diameter of a wire using this particular interference phenomena? Got the idea, no? So this diameter of this particular wire has to be determined. So there's a wire whose diameter has to be determined, which is placed between the two glass plates. Because of this wire placed between the glass plates, so then the upper plate will have some inclination theta, and usually what is the thickness of wire or the paper will be very small. So theta we can expect to be very small. Then, okay, now let's see that one. For normal incidence of the light of wavelength lambda. So let the phase of that be 0. So it will incident normally. So it will go there. A part of ray, what happened? A part of ray. So the again it will be incident. So now here it will encounter a glass and air interface. A part of ray will be reflected, and a part will be transmitted. We know that the air film is what reflecting it. So the phase angle will be 0. And the refracted ray will flow in air, and air will get reflected by glass plate, and the glass plate and the ray now get reflected by glass plate. So when a ray reflected by denser medium should undergo phase change of pi radian, so the reflected light here will undergo phase change pi radian. Again, a part of ray will be reflected, part will be transmitted. We are bothered about transmitted. So finally, the ray B will emerge with a phase angle pi radian. Since it's a normal incidence, we need not to bother anything here, the reflected ray. So now there are two rays are there, A and B. Shall I say A and B are reflected by air only, by air film, due to air film. The upper part of air film will produce a ray A, and the lower part of air film will produce ray B. So this corresponds to air film. We have to think in this way. So this light is incident normally. Fine. So when it encounters here, it encounters an interface, air glass interface. So the ray moving from glass to air, a part of ray will be reflected, part will be transmitted. The reflected ray will have a phase angle of 0, this one. Then because as it is reflected by rarer medium, then again this will, a part of ray will be reflected, will be transmitted. We are not bothered this reflected one. Okay, the transmitted ray will not have any phase change. So the same phase zero, the ray will acquire. What about this refracted ray in air? The moment as it moves here, it will encounter a denser medium. So it will be reflected by a air glass interface. And because of that, it will acquire a phase change of pi radian. Why pi radian? Because glass is denser, air is rarer. When a ray reflects by denser medium, it will undergo phase change of pi radian. So now the ray will undergo refraction. Due to refraction, no phase change. Again, refraction, no phase change. Finally, it will emerge. So ray A and B. So now compared to ray, let's compare the phase difference between these two rays. So not only at one point, okay, the rays are incident normally on this upper glass plate. Then some red color, green color, blue color, some three set of rays is what I'm showing. So we'll all will have the same path difference. No. So this red color weapon will almost what will happen? Will not traverse any length in air. The green color, it will traverse some length. What about the blue color? It will traverse some length. So the rays which are incident at different parts on the glass plate will traverse different length in air film. You can see it will traverse this much of length. What about this? It will not traverse any length in air film. What about this? This will traverse some length. So different parts of incident rays traverse different length in air film. So different path length they'll acquire. So if the path difference equal to n lambda or 2 n minus lambda 2, s, the different order of interference is what I'm going to notice here. Because of this, the path length of the different rays will be different in air film. Okay, let's come for the mathematics. Derivations, we'll get into derivation. Okay, no. So now, what is that? The wedge-shaped air film is what? Something very important. Due to that is what? We can see that one. So now let's go for condition for bright fringe. Okay, let's compare the path difference between rays A and B. Then the total path difference. Path difference should be due to equal to path length. So how much of path length the ray B will cover in air? Theta is very small, so we can write as 2t is what it will cover in air. Optical path length will be 2 mu t. Of course, it's in A, no, later on I'll write it, mu equal to 1, I'll write it. Then the ray B is having a phase angle of pi compared to ray A. So because of that, this lambda by 2. Then we are searching for maxima and lambda. And what happened mu? Mu equal to 1 for A. So this will become n minus 1 by 2 lambda equal to 2t. So what should be the thickness of this one? Thickness of this will be, air film will be 2n minus 1 lambda by 4, where n is equal to 1. Let me write it below. What are the values of n? N we can pick up 1, 2, 3, 4, and so on. So what is this T? Thickness of air film. Similarly for dark fringes, what we can write here? Condition for dark fringe, delta x. Delta x should be equal to 2n plus 1 lambda by 2. So therefore this will become n lambda is equal to mu t, where n is equal to 1, 2, 3, and 4, so on. Even if the ray is not incident at an angle, then cos r will come into picture. Usually it will be normal incidence only, what we discuss this one. So these are the thickness. Okay, now what was our question? Our question was to calculate the diameter. No. Okay, now why I'm bringing this equation? So what is the finally what is the purpose of this? Like what you are bringing. Now, if you look at the set of equations, how to find out the diameter of the wire? So this was our primary question. No, how to get that one? How to get the diameter of the wire? From where to bring the diameter of the wire? Now, why the order of interference will come? Yes, definitely as you put n equal to 0, what is the thickness of air film? Will be 0. I think I have to show you this part. Let me adjust the content. Yeah. At t equal to 0, so put n equal to 0. N equal to, so like n equal to 0. So what do we get? We get the dark fringe where t equal to 0 will be there. Put n equal to 0. N will start with 0, 1, 2, 3, and 4. For n equal to 0, t equal to 0. So like that, as the thickness of air film increases, the order of interference will increase. So what are this? This is the value of n. N equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4. So as the thickness of air film increases, the order of interference also will increase. So on what basis I can look at this t equal to n lambda by mu, I can put it. But what was our question? Our question is to get the diameter of the wire. So if you look at this triangle, look at this triangle. This is capital D. This is T. This is X. This L. This is theta. So from tan theta equal to T by X equal to D by L. D by L. So where X is equal to L T by capital T. D is the diameter of the wire. So now put it here. What is T is equal to? What is T is equal to? T equal to, shall we write it as equal to n lambda? So sorry. There should be 2t here. Okay. So some correction I'm making it, because mu equal to 1 for air. This will be n lambda by 2. Okay, this will be 2t. Now t is equal to what we can write? N lambda by 2. So this will be n lambda L by 2t. So what I got the position of X, this one. Okay, lambda, all these are terms are constant. Okay, let me calculate the fringe width. Put X equal to n equal to 1, n equal to 2. The fringe width should be 2 lambda 2L by 2D. So now, so can you, do we know L? S, I know the length of the glass plate. I know the wavelength of incident light. Then I know the fringe width. Fringe width, how do I calculate? Yes, I'll take help of traveling microscope. measured using traveling microscope. So I'll take traveling microscope. I'll focus on this interference pattern. I'll measure this fringe width. What is the fringe width? Usually I should measure the distance from the center of the bright band to center of the next dark band, or center of the dark band to center of the next dark band. Or else, so one distance, one width of one bright and dark band will be one fringe width. But practically what is the method? The method is from the center of, this is the fringe width. So using traveling microscope, I'll calculate the fringe width. I know the length of the glass plate. I know lambda. Okay, this one. So with the help of this, we'll get the diameter of the wire. So what is here? What are the assumptions we are making? It D will be very much less than capital L. Similarly, the T, what we say, it will also will be very much less than capital L. So what is D now? Finally, the D is the diameter of the wire. Very almost accurately we are able to measure. Okay, this is about the interference in the thin wedge-shaped film. The wedge-shaped film is air. It can be even some liquid. In that case, when the mu of a liquid is what you are going to add up here. Okay, that one. Since the air film, the wedge-shaped film was air, no, so therefore the mu has become 1. If some other liquid come, no, you bring that mu into the picture. Got this one? Okay, no, we'll end up the class here. Okay, fine. So in today's class, what happened? We had a discussion on the this one. The first one was like a